Okay, so last time we talked about minerals, and I hope there'd be a couple more minerals here for us. They're coming. Okay. So one of the minerals you're going to see is a nice big crystal of halite, this big cube that reflects the detailed order of all the atoms that are organized. And because I wasn't sure that any of you went and bought microscopes to look at salt in your dining halls, another great experience. So we got some table salt here and we put it under this microscope, and now it's being put up on the screen here. And lo and behold, they're little cubes. And those little cubes, if you broke them up into still smaller pieces so you had very fine-grained salt, they'd still be little cubes. They're always going to be little cubes. And if you make a big halite crystal, it's going to be a big cube. And that is reflecting the atomic structure of this mineral, where you have sodium, chlorine, sodium, chlorine, sodium, chlorine, all arranged in this beautiful cubic form. And it's reflected macroscopically under a microscope like this, or in the big crystals that you'll see in a little bit, all relating to these laws of symmetry and the way atoms are organized. And now, in addition to the minerals for life, we have to have organic molecules. And organic molecules have carbon-hydrogen bonds in them. The simplest one is methane. That's shown here on the left, a carbon with 4 hydrogens around it. And then you have ethane and propane, and you can keep on going, making the carbon chain in the middle longer and longer. And there are tons and tons of organic molecules, hundreds of thousands of them. And when now astronomers look out in space, they're finding all kinds of organic molecules. All these things in red and blue are the list of organic molecules that have been found in interstellar clouds. And so you're finding all these ingredients for life distributed throughout space. After all the elements have formed and they come together in molecules, they make minerals and they make organic molecules. And the minerals will be the stuff of planets, and the organic molecules will be the stuff of life. And it's happening today in clouds like this, which is the Orion Nebula. Here, supernovas are forming the elements. You have solar systems happening today. You have all the necessary building blocks for planets and life forming in these clouds, forming the molecules that will ultimately lead to solar systems that billions of years down the future may lead to other creatures like us. So, in our lectures thus far, we've moved from the stellar reality of temperatures of tens of millions or even hundreds of millions of degrees, where the nuclei of atoms interact to form different elements. Elements are created and destroyed all the time. It's normal. To a planetary reality, where we have temperatures of hundreds or maybe a few thousands of degrees, and there atoms are neither created nor destroyed. Atoms are permanent, except for the rare radioactive element. And these permanent atoms form molecules, and those molecules then are going to make up the structure of the planets and the structure of life. And we know those molecules form in interstellar clouds shortly after supernovas distribute the elements, because astronomers can look at those clouds and see they're there. They see minerals in the interstellar clouds that are the same minerals we find on Earth. And they see organic molecules that are the fundamental building blocks of life. So both these things are present in the clouds, and those are the raw materials that are needed to make habitable planets when these things come together to make larger objects in solar systems. And we're going to be talking about the origin of solar systems today. So these building blocks for planets and life are common and distributed in abundance throughout the universe. Everything we need is there, waiting to be put together in the right way. And now what happens to these molecules will then determine how solar systems form, how planets behave, how planets evolve, because all of the stuff that happens is going to be involving interactions among electron clouds that are occurring on planetary surfaces and interiors. And these will depend on the physical properties of various minerals. Okay, so here's a halite crystal. Pretty cool, huh? If you don't believe it's halite, you can lick it. It has little other crystals growing out the side of it. But And you break this up, and I won't, because when they get this big, they get valuable. But if I cleaved it, I could get two things. I could make it into cubes. I could crush it, and I would get little tiny cubes like you see in a thing of Morton salt. And it has a certain density. You can feel how heavy it is. And then here's something of about the same size that is another cubic crystal called galena. And so galena is a lead sulfide. This has other things in it too. But if you feel these, you can feel a difference in density. Or we could take this thing, solid gold. It's about a pound. So, I don't know, about $20,000 worth of gold right here in my hand. So I'll let this hand around, and don't be tempted. Okay. And you'll feel this little tiny gold object and this big, large object of halite, and you'll see they weigh about the same. So these physical properties in these molecules are going to help us answer all these kinds of questions we're going to be addressing in the next few weeks. How the Earth formed, why is the Earth made of rock and metal, why is Earth different from Jupiter, why does the Earth make layers, and why do they have the composition they do, and all this is fundamental to Earth structure, which we get to next week. And that depends on the properties of minerals, and the two we're going to emphasize and go over today are the density and the volatility. Anyway, gold is dense, as you can see, and when you look, and it's made up of gold. And sodium chloride, which is the salt, is just sodium chloride, and it's light. So why? Why can you have different objects be of such different densities? And that's going to be controlled by the average number of particles in the nucleus, as well as a little bit on how closely the atoms pack together. So when you take gold, or you take lead, say, lead has 206 nuclear particles in its isotope. So you take hydrogen, it only has one. And all the mass of the element resides in the nucleus. The electron cloud weighs essentially nothing. And so when you have an atom of lead, it weighs 206 times as the atom of hydrogen. Now, it also has slightly more electrons, so it has a bigger electron shell, so it's a little bit bigger. But the increase in size doesn't compensate for the change in the number of nuclear particles. So if you take a molecule like water, it has 2 nuclear particles in the hydrogen and 16 in the oxygen. So there are 18 nuclear particles, and you have 3 elements, so we divide by 3, and you get an average of 6 nuclear particles per atom in the molecule of water. Okay, so let's take carbon dioxide. Well, carbon is 12, oxygen is 16, so that's 44 divided by 3, and that's about 15 nuclear particles per atom. So it's going to be denser. So the liquid carbon dioxide is much denser than liquid water is because it has more nuclear particles per atom. And if you take a bucket of water, you can carry it around, or you have your nice bottle of water within your backpack and you carry it around. If you had a bottle of lead in your backpack would be very difficult to carry because the lead would be so much denser than the water, because the lead, pure lead, is 206 particles per atom, and so that's 30 times denser than the water is. Now, it's not exactly like that because of the change in size. So here is the density of various materials, and here's the average number of nuclear particles per atom, and that one-to-one line is if the atoms were the same size. And you see that as your nuclear particles per atom goes up, your density goes up, but not quite linearly like that. That's because the atoms are getting bigger. And of course, iron metal which is iron 56, is going to be much denser than carbon dioxide and water. And if you take something like quartz or a silicate, this is 28 and 2/16, so that's 32, 42, 52, that's 60 divided by 3. That's about 20. So we can make a list of all the things and what their densities will be on this basis. We can have uranium, which is really dense, and gold, which is really dense. Lead would be out there. Iron metal is about 4 times less dense. And then you have the silicates, and then you have things like ices, water, and CO2, and so on. All of them with different densities. And in this way, you can see what controls the density of materials. It's the number of nuclear particles there are in that little tiny nucleus that resides in the center of the atoms that make up the molecule. We okay? Okay, so magnesium is 24, and there's another silicate called forsterite that has a formula like this, and it has an end member with which it alloys, makes a solid solution that has a formula like that, 2 irons. Which of these has a higher density? Can you see this, or is it blocked? Yeah, the iron would. Why? Because it's got 56 nuclear particles per atom. And the magnesium only has 24 nuclear particles per atom. So this part of the mineral formula is the same. The number of atoms is the same, 4, 5, 6, 7, 4, 5, 6, 7. This is the same, but these molecules, these atoms, are much denser than those atoms. So the density of the iron form is much denser than the magnesium form by this same principle. So here's a list of a bunch of common, or a bunch of interesting molecules or metals. And here are the nuclear particles per atom. You see gold is 197, and its density is 17. And the halide, I think, has a density of about 2, so the gold's 8 times as dense. And you can see the number of nuclear particles per atom as it goes up, the density goes up. It's not perfect, but it's pretty good. So in this way, you can estimate pretty well what something is made up of by just seeing how dense it is. How dense is it? Do I know what the most common elements are? Could I maybe estimate what it might be made up of? If I had you lift 2 buckets, one with iron, or 3 buckets, one with iron, one with lead, one with water, and one with air, and you lifted them up, you would immediately know which one was which. So density is also a primary way that things organize themselves. We float in water because we're less dense than water. Rocks sink in water because the rocks are made up of silicates, and they have higher densities than water, and so they sink to the bottom. And wood is made up of organic molecules with a lot of air and stuff in between them, so the wood is light. So if you throw wood, rock, and water into a bucket, the wood floats on top, the water's in the middle, the rock is beneath the water, and you're getting a complete stratification and organization on the basis of density. And that's just how planets organize themselves as well. All right, the second thing we're going to look at is volatility, and that is a word that relates to states of matter. So you're familiar with solid, liquid, and gas. The most common state of matter in the universe is plasma. So this says basically how many particles there are in a given volume down here, and that temperature is how hot it is. And we live over here where you have solid, liquid, and gas. But as you get to very low pressures out in space, or you get to very high temperatures, like in stars, you don't have solid, liquid, and gas anymore. You have this other state of matter called plasma, which is not that familiar to us, but which we see, for example, when we see fires. when we see a fire or we see a neon lamp. Now, these states of matter are important for habitability because all the different molecules turn into gas and liquid at different temperatures. And we call elements or molecules volatile elements when they turn into gas at low temperatures. And we call them refractory elements when they turn into gas at high temperatures. So this relative volatility is going to play a very important role in planets, and as you'll see in a minute, in the origin of the solar system. Volatile elements, liquid or gas at low temperature. Refractory elements only change to a liquid or a gas at very high temperatures. So here's CO2. And you can see it transforms to liquid and gas at around minus 56, depending on the pressure. And if you compare that to iron, this is the melting diagram for iron. This is temperature. We're up here at 1400 degrees, and this is all solids down here, and it transfers to a liquid at 1400 degrees. So the iron is much more refractory than CO2 is. And CO2 turns into a gas at room temperature, and water is a liquid at room temperature, so which one is more volatile? CO2 is more volatile. And here we have CO2, and it's changing into gas. And you can also see that the gas that it changes into is dense. It's denser than the atmosphere. That's why it'll form this nifty little cloud. Or if you do theater productions and you use CO2 to, make a cloud on stage, the cloud will stay near the bottom of the stage because it's so dense. You can blow on it. So this is turning into a gas at low temperatures. And so we can test the volatility of different things. And so I brought in some coins, partly because, I just like to burn things up. So here's a nickel. It's got sodium on it. The sodium is more volatile than nickel, so it's turning into a gas. Now we're beginning to see the black body radiation coming off the nickel. But no matter how high I heat it, it doesn't melt. So we see sodium is more volatile than nickel is. The nickel is very refractory. Here's a penny. Copper has a high melting temperature. Sodium, volatile. It's going to be the same color as the nickel because of the black body radiation. Very refractory. Here's another penny. What the hell? Wait a minute. Let me try another penny. So there was this one penny that just melted, and then we have this penny which doesn't melt. What's going on? A penny is a penny. And yet, when you look at these pennies that I melted, they turned into this liquid goo. And I just don't know how hot it is. So, see, it turned into this liquid goo that covered all the other coins I put in there. It's sort of gray colored. It's much more volatile than copper. It's not copper. What's it made of? It's zinc. So zinc has a very low melting temperature. So all pennies before 1981 were made of copper. And all modern pennies are made of zinc, a much more volatile substance. And they just cover them to make them look like copper, but they're not copper anymore. Why did they do that? Because copper is too expensive. Okay, so a copper penny is actually worth 3 cents. The copper in it is worth 3 cents. So I can see maybe your entrepreneurial eyes are starting to, things are going off in your head. You could somehow construct like machines in supermarkets, okay? And you have people, you say, come in, give me all your pennies. So they bring in, they give you all their pennies, and you have this machine that sorts them by density, because copper and zinc have different densities. And, you know, you collect millions and millions of pennies by this method. And then you take the copper pennies, and you have $1 million worth of copper pennies, and you turn them into copper ingots, and you sell them, and you get $3 million. Fantastic business opportunity. And so because it's such a fantastic business opportunity, Congress passed a law saying that it's illegal to deface currency. So if you melt down the pennies, you're defacing currency and you can go to jail. So different elements have different melting temperatures, different volatilities. And volatility is also how matter becomes organized. And we're going to see that this simple demonstration that we just looked at is going to be important for the origin of the solar system. Oh, there's one other thing that I have that's even more volatile than CO2. And CO2 is a gas, but nitrogen turns into gas at much colder temperatures. So this is liquid nitrogen. See, it makes this. Does anybody want me to pour liquid nitrogen on their arm? You do? Okay. Turn your hand over like that. Okay. Ready? Want to try? Yeah. So, don't take a shower in it. No, that's not good. So the reason why it's, if you go to, when you get older and you get skin cancer and stuff, you'll go to a dermatologist and they will remove your skin cancer with liquid nitrogen. But then they have concentrated liquid nitrogen and they'll spray it directly on the cancer on your skin and they'll kill it. But with this liquid nitrogen, when it hits your skin is so warm, it immediately vaporizes it. So you have a vapor bubble between the liquid nitrogen and your skin, which allows you to not suffer harm. Where's the gold? Okay. Has it been all the way? Okay. So I'm gonna pour some liquid nitrogen in here. So it's boiling in there. It boils vigorously at room temperature. You can see the line of liquid nitrogen on the outside. And wait a minute. What's happening here? Can you see underneath it like a stream of liquid coming off it? What is that? Liquid nitrogen would freeze water like that. You see that liquid coming off? Well, will somebody come up and help me? Will you come up, Araf? I want you to light the candle. No, this isn't to do something. I'm not going to harm you. You just light what looks like water, or move the candle so it's right under that little stream. Can you move the candle? Perfect. Not putting out the candle. In fact, it didn't put out the candle at first, okay? It was actually making the candle sputter a little bit more brightly. So, what is this? You can hear it. You hear it? Dropping? What is that? Liquid oxygen. So the oxygen is less volatile than the nitrogen. So the nitrogen is making the outside of the can so cold that the oxygen in the air is turning into a liquid and dropping down. And that's why if I had a more vigorous candle, the candle would really sputter. So we have this sequence of things where we saw these changes in melting temperatures, and we have a volatility sequence. We saw that we had iron and copper up here somewhere that were pretty high, and then we had zinc. And then we know as we go down in temperature, what do you think? Do you think alcohol is more or less volatile than water? More volatile than water. So we'd have water here, and then we'd have alcohol, then we have CO2, then we have oxygen, then we have nitrogen. We'd have noble gases way down at the bottom, down here, helium. And so we have this sequence of increasing refractoriness going up, and as we go down, we have increasing volatility. Apologies for my handwriting. And so if we, say, had a temperature like we have in this room of 25 degrees centigrade, we know that these are gases, and we know that these are liquids, and these are solids. And that's at 25 degrees C. If we went down to 0 degrees C, then our solid line would move down, because our water would turn into a solid. And if we went down to still colder temperatures, our alcohol would turn solid. And still colder temperatures, our carbon dioxide would turn solid. And if we went down near absolute zero, all this stuff would be solid. Or if we increase the temperature even more, we can change zinc into a liquid, and we're only left with these at the top. So if you, for example, wanted to do a really good job in cleaning out this room and making it really get rid of all the stuff in it, you could just heat the temperature up to 1,000 degrees. And you heat it up to 1,000 degrees, we all disappear, we're vaporized. So all the chairs and the fabric disappear, the lug goes, everything. You set up a fan and knock it all out, and the room is just left with metal in it, metal and rock. That's it. That's all you have left. Or if we decided that we wanted to collect everything that was in the room, we would lower the temperature way below the freezing point of nitrogen, say, and all the nitrogen and water and carbon and oxygen in the air would all turn into solid and would all accumulate as ice on the floor. So what is solid, what is liquid, what is gas depends on the actual temperature, and we're going to see how that relates to the solar system, because you have the sun, you have the inner planets, and you have the big outer planets, and this right here is the snow line, which is a temperature boundary between when low melting substances that are volatile, like carbon dioxide and ammonia and water, they're solid out here. And so when these things collect to form planets, they collect all that stuff. But on the inside of this line, it's too hot. all of this stuff that's collected in the big planets out here is just gas. So when these planets formed, they're just made up of rock and metal. And out here, you're going to have rock plus metal plus all the ices. And so there's lots of this stuff around because you have things like carbon and oxygen, which are two of the most abundant elements in the universe. And so there's lots of those. And you get big, fluffy, light planets on the outside and small, rocky, dense planets on the inside. Okay, so let's go through this origin of the solar system in more detail. In olden times, or if you go camping, or somebody was mentioning to me going to the Atacama Desert in Peru recently, and there's no civilization up there. You're up at 18,000 feet or something. And so you look up and the sky is just absolutely filled with stars. So that's what the sky actually looks like. You don't see it like that. We don't see it like that living in cities, living inside our illuminated houses. Sometimes we're not even aware if there's a moon in the sky. But ancient people did, and when they looked at it, sometimes they would see meteors coming in. So this is a shooting star. Sometimes it reaches the Earth's surface and turns into a meteorite. So those are messengers from outer space. And this is a time-lapse photograph. So you can see how the stars are moving in a circle. They are moving along lines. They're not moving much over here, but they're moving a lot over here. That's because they're all rotating around, apparently, the North Star as far as we can see them. And ancient peoples paid a lot of attention to this and built observatories like Stonehenge, where if you try to go to Stonehenge on the summer equinox, there's a huge traffic jam, because when you stand at Stonehenge at one particular spot, on exactly dawn of the summer solstice, you see the sun rising through the pillars. The stones are perfectly aligned to be able to tell what date it is, and relating the people on earth to the heavens above. Now, strangely, there are other objects in the sky that move across the stars. And they're also brighter than the stars, mostly. So they're in different places in the heavens each night, and they generally follow the track of the sun. So the sun went down like this. Now sun is going down. This is the moon down here. So you have the sun down here shining up on the moon, so it's a barely new moon. And then along the same track, you see moon at different dates, and you see these other things called planets that follow the same track as the sun moving across the sky. So the sun, the moon, the planets are all moving in the same track across the sky, and that means they're all in a single plane. And it's one of the regularities of this location that we live, that with the exception of Pluto, which was demoted to non-planetary status a number of years ago, and it's slightly offset, but the rest of the planets, shown here by these various different symbols, are going around the sun coplanar, all in the same plane. And all moving in the same direction. So they're all moving in one plane around the sun, they're all moving in the same direction around the sun. It seems like they're related to one another. So if you want to ever know what the position of the planets is on a particular day, you can go to this website. So you have that written down there. And so by looking at this, you can say, oh, where is everybody in the solar system right now? And you can look on this and tell. And if you look up at the sky, you can see them. So this is just a table. I'm not going to go through a table in detail. But I'm just going to put down these lists of things that we know about the solar system, that all the planets lie close to the plane of the ecliptic. All of them rotate in the same direction going around the sun, and they're evenly spaced. These are a graphical presentation of the numbers that were in that table. So on the horizontal axis here, you have the order of the planets. So 1, 2, 3, 4, 5, 6, 7, 8, 9, or 8. And up here you have the distance compared to the Earth. The Earth is at 1, so it's multiples of the Earth. And you can see that this shows a straight line, but if you look carefully at this, you see it's a logarithmic scale. So that means each planet is a multiple of the distance of the previous planet from the Sun. And the multiple is a number of about 1.6. That's called Bode's law. So Earth is 1, Mars is about 1.6, the asteroid belt is around 2.5, Jupiter is around 4, and so on. And you can see what it would be if it were perfect would be the dark dots, and the diamond shapes are the actual observations, and it's remarkably regular. Just remarkably regular. So we can add that to our list, that the planets are not evenly spaced, but regularly spaced. And this is the diagram I drew on the board, where you have these little tiny inner planets. The asteroid belt separates them from the big giant outer planets. That's a great regularity of the solar system. Now, of course, we can't show these to scale, because if we did, Pluto would be up in Arlington somewhere. I have my directions right. Anyway, be very far away from here. So we have to compress them all like this so you can actually see them. So we need to explain all these features. Why are the planets evenly spaced? Why are they all coplanar? Why are they all rotating in the same direction around the Sun? And why are the inner planets small and the outer planets big? Well, we can determine the densities of the planets by looking at the moons of the outer planets. So here's Jupiter, and here are 2 moons of Jupiter, Io and Europa. And by looking at how rapidly they rotate around Jupiter, you can determine what Jupiter's mass is, and you can measure Jupiter's size. And when you know the mass and you know the size, then you know the density, because the density is mass per size, or mass per unit volume. So this is cool. So when you have astronauts circling around the Earth, and the astronaut is there and weighs 100 kilograms or something, and he's in a space station, and the space station weighs many tons, but he goes out of the space station, they keep rotating at the same speed. And he needs to fix something on the outside of the space station, so he has a screwdriver, and he pulls his screwdriver out of his pocket, and he holds it, just puts it out in space next to him, and they're moving around thousands of miles around the Earth, but they move at exactly the same speed. It's so handy in space. Your tools, you don't have to put them down on something. You can just put them right next to you in the air, and they just stay there. So independent of mass, things rotate at the same velocity. So we don't need to know the mass of these moons. You just need to know how fast they're rotating around their planet to determine what the gravitational field of the planet is, and therefore what the mass of the planet is. You can do that for all the outer planets because they all have moons. You can do it for the Earth because the Earth has a moon. You can do it for Mars because Mars has a moon. You can't do it for Venus, so for Venus's density you have to see how Venus's orbit is perturbed by other planets. All right, and when you do that, you learn 2 things. You learn what the total mass of the planet is, and here you have the inner planets on top with very small total masses, and you have the outer planets down here with very large total masses, except for Pluto. And you can determine their densities, and there you find a strange thing, that the densities of the inner planets are very high, and the densities of the outer planets are very low. They're about the same density as water, a density of about 1. Now, the density of the inner planets is denser than rock. Rock has a density of around 3. That's rock. And the inner planets are more dense than rock. And the outer planets are much less dense than rock. So it's weird. You have much more mass, but much lower density in the outermost planets. Okay. Those are more regularities of the solar system. We have other representatives of the solar system that come in and visit us, which are the meteorites. And many of them that land on Earth are very, very old when they're dated, 4.55 billion years old. And all the meteorites that are old like that have these little globules in them that are a couple millimeters in size or a millimeter in size. And these little round globules are called chondrules. I don't know why they have that name. But because they're called chondrules, the meteorites that contain these little round objects are called chondrites. And the only way people think that these kinds of little round spheres of rock are made is as droplets in outer space. You can't make them on Earth's surface. Okay. So they come in, they're 4.55 billion years old. Here's a diagram showing 20 or so different chondrites, and they all have the same age. They all formed at the same time within error, 4.56 billion years. And if you look at the composition of the chondrites, and you compare it to the composition of the sun, you find that the relative abundances of the elements in the chondrites are the same as the abundances of the elements in the sun. The sun's elements are determined by looking at its spectrum. Of course, they're not the same in terms of hydrogen and helium and the noble gases and things like that. But the relative abundances, the ratio of silica to iron and iron to copper and lead to zinc and so on, they're on this one-to-one line. So these chondrites coming in are representative of the sun. The sun is made up of the same kind of stuff. And they're all old, really, really old, the oldest things we know of, and they're all the same age. So, this is all the lines of evidence for the scientific detective to try to work with. We know that they're all the planets. Didn't go backwards, sorry. We know that all the planets lie close to a single plane, which we call the ecliptic. It's the equator of the Earth. All planets rotate in the same direction around the sun. The planets are regularly spaced. There are systematic differences in planetary size and density, with inner planets being small and dense, and outer planets being big and light, big and less dense. And the meteorites in the sun have similar chemical compositions, and we also can date the Earth and the Moon in meteorites, and they're all the same age. And we think the Earth's composition is more or less similar to some of these meteorites. So, what's going on? Well, using the rules about density that we talked about earlier, we can tell something about what the planets are made of by this rule that we talked about at the beginning of the lecture. And so, here are the metal abundances in chondritic meteorites, and you can see they're mostly made up of magnesium, silicon, and iron. And oxygen would be the other thing that's a major element, but because it's not a metal, it's not listed in that table. And when you look at the minerals that are made up of these kinds of elements, you see that things like olivine has a density of around 3. That's the mineral formula I wrote on the board earlier up there. That has magnesium and silicon in it. This mineral has a density of around 4. That you have these other oxide mineral phases with densities in the 3 to 5 range. None of those are the right densities for the outer planets. Iron is really dense, 7.5. And you have things like water and calcite that are really light, like around 1. And so, if we look at densities, then we can say, here's Earth and Venus, there's the Moon and Mars, here's the Earth crust, they're iron meteorites, and way up here at 1 are the outermost planets. So, you have very dense things made up of metal, you have silicates, which are around here, around 3, and you have most all the inner planets, which are in between the two, and the outer planets that are much lighter than all of those things. So, what can the outer planets be made of? And you look at the densities of the ices of the elements that are very abundant during nucleosynthesis, like methane, ammonia, water, CO2 would be there. And this is their number of nuclear particles per atom, and here their densities, very light. You take the oxides, like quartz and this magnesium thing, densities of around 3, and metals around 8, and these are the alpha particle nuclides. Carbon, hydrogen made during the Big Bang, oxygen, silicon, magnesium, iron. Those are all the things that are made in superabundance in the universe, and therefore planets have to be made up largely of those elements. And so the inner planets then would be inferred to be mostly rock and metallic iron, and the outer planets are mostly ice and gas. And the differential volatility, that is, this range that we were talking about, would explain why you have those differences, why out here you collect everything, the rocks and the metals plus ice and gas, because these things get such big gravitational fields. And inside here, you don't get to collect any of the ice and the gas because they're small, they're high density, and they only collect the rock and the metal. So all of these things then come together into related to what we see in these interstellar clouds, that you have a body of gas and dust, which has a little bit higher density than its surroundings. It's spinning a little bit. And so there's a gravitational attraction towards the center, and so things start to collect together. And it's spinning, and as it spins, material flows towards the center, and also it flattens out into a disk. But because so much material is collecting towards the center of gravity, you get a ball in the center and a flat disk going around the side of it, all rotating in the same direction. So this disk is the future solar system, and the blob in the middle is the future star, the future sun. So the cloud spins rapidly, and if you've ever worked in a pizza shop, like I did when I was a little older than you guys, you're able to make things that are really flat and thin by spinning them up in the air, but there's no gravitational attraction, so you don't make a sun near the center, but you're able to make a flat disk by taking this round blob and spinning it, and that's what happens in the interstellar cloud. And then a sun will be igniting in the middle gradually, and when the sun ignites, it becomes very hot. And as you get farther and farther away from that star, it gets colder and colder. And so close to the star, you have high temperatures, and far from the star, you have cold temperatures. And the little particles start to coagulate in little centers of gravity in that disk, and you get things that are not yet planets, but are called protoplanets, where these things come together to form things that are like about the size of the moon. And then those all bang into each other in massive collisions to create the final planets that we see. And each planet then acts like a kind of gravitational vacuum cleaner in its orbit. So you have two things orbiting, and they're competing for material. And so as they move around, they gradually clean out all the material in between them and end up with this regular spacing. So we can see this happening in other places within our galaxy. So these are images of what's been seen in the Orion Nebula of, you can't really tell from looking at these, but there's a star and there's a disk around the star where the planets have not yet formed. So we can see indications of this happening elsewhere. There are disks around young stars. And so we think there are solar nebulae elsewhere in our galaxy where solar systems are forming currently. Now, you can also calculate computer models to do this. So the computer models are limited in the number of objects they can deal with. They can deal now with about 1,000 objects. So you take 1,000 objects rotating around a sun, and then you just press go, and all of them rotate around the sun, and they interact with each other, and they bang into each other, and when they bang into each other, you make them stick. And in this way, you can simulate what happens for the formation of a solar system. But the computational challenge is huge, because every one of these 1,000 objects is exerting a gravitational effect on the other 999. And so at every time step, you have a huge computational load, which limits the efficacy of these kinds of calculations. Nonetheless, when you do those, then you can make thousands of solar systems, and some of them look like ours, and some of them don't, suggesting that there'll be a whole variety of different kinds of solar system types. So the takeaway messages then from this are that solar systems are beginning because of gravity. Most stuff ends up in the sun. A disk is formed because the big ball that originally starts is rotating. Little planetary cores form in the disk because the rocks hit or gravitationally attract each other. And if there's ice around where it's cold, far from the star, the cores are bigger. And if they get big enough, they'll suck gas out of the disk and form giant planets. Moons can form by collision or capture and mini disks. So the moons around Jupiter probably formed by a disk around Jupiter, just the way the planets formed by a disk around the sun. And the observations generally agree with the theory that you can't see that word, it says observations. And the simulations also agree with the theory, but they can't model everything at once, and there's some problems, like they take too long. And also, there are going to be millions of objects of small size, and they can only do simulations with large objects. So, solar system formation appears to be a very natural process. We see it happen in our solar system. We see all kinds of regularities associated with it that make sense. Now, recently, we can see solar systems forming around other stars within the Milky Way. So we know that solar system formation is something that is a common occurrence. We can model it, beginning to model it pretty well. So that's giving us more information about how solar systems might actually form. And so when you do the statistics on it and you take this understanding, it means that there are trillions and trillions of solar systems within the universe, billions and billions of solar systems within our own Milky Way galaxy. And we're just one example of this very common universal process. Now, when we see what we've done thus far, we see the Big Bang is everywhere. We see that element creation is the same everywhere, and the same elements are everywhere, and the same elements are made in abundance everywhere. We see these elements form molecules that follow universal laws like symmetry in the electron cloud. So the same molecular formulas that I can write up on the board up here with CO2 and water and the silicates and all this, well, they're going to be the same minerals everywhere. In some distant classroom in the Milky Way galaxy, there's a bunch of aliens sitting down, and they're holding gold coins in their hand or looking at halite crystals. They're looking at exactly the same stuff that you're looking at because the same laws apply everywhere. And maybe they have some crazy professor lecturing to them, or maybe they're much more advanced than that, so they have other ways of learning that are much more efficient. But the same principles, the same materials apply everywhere, and solar systems form everywhere. So then the question is, once you form a solar system and you form a planet like Earth, what happens to it? And are the things that happen to Earth also likely to be things that happen everywhere in the universe or not? And we'll move on to that next time.